Good afternoon. So let us start our lecture today. So let us fix the mistake that I made in the previous lecture. Could you hear me clearly? Could you hear me? Yes? No?
Yes.
Okay, good, thanks. So in the previous lecture, we were trying to solve the show that a plus 1 over 2 to the power p plus a minus 1 over 2 to the power p is smaller than or equal to a to the p plus 1 over 2. So p is a number which is bigger than or equal to 2. All right, so this is what we were trying to solve. In the previous lecture, we used an inequality of the type alpha to the p plus beta to the p smaller than or equal to alpha square plus beta square p over 2. So this will be our homework this week, and the deadline will be next Friday. All right, so you can try to prove this inequality and then take a picture and send it to me, right? Now, suppose that we have this inequality already. How can we show the first inequality? What we do is to replace alpha to be this guy and beta to be this guy. All right, so alpha will be a plus 1 over 2 and beta will be a minus 1 over 2. Right, so now we want to plug this inequality, these two values for alpha and beta into this inequality. So then when you use it, you're going to have a plus 1 over 2 square, which is alpha square, a minus 1 over 2 square, which is beta square, and then you're going to have b p over 2 outside, right? So what is a plus 1 over 2 square plus a minus 1 over 2 square? So a plus 1 over 2 square plus a minus 1 over 2 square will be a square plus 2a plus 1 plus a square minus 2a plus 1 over 4, right? And when you do the expansion, you're going to get a square plus 1 over 2. So basically, the quantity inside will be a square plus 1 over 2, right? You replace this value into this, you get a plus 1 over 2 to p plus a minus 1 over 2 to the p is smaller than or equal to a square plus 1 over 2 p over 2, right? So so now the next step is, okay, you want to show that this is smaller than this, right? But you already show that this is smaller than this one. What you have to prove next is to compare this guy with this guy. All right, you have to compare this one and this one, a to the p plus 1 over 2 and a square plus 1 over 2 to the p. In other words, you're going to have to show that a square plus 1 over 2 p over 2 is smaller than or equal to a to the p plus 1 over 2. Now, to show this inequality, I'm going to consider this function. All right, so in the previous class, we were trying to do this, and we was thinking that this is a monotone function, but no, let us compare, let us do the computation, right? So what is the derivative of this function? So f prime of a will be p over 2, right? A square plus 1 over 2, p over 2 minus 1. And then you take the derivative of the guy inside, which is a square plus 1 over 2 prime, right? The derivative of a p to p plus 1 over 2 is going to be p over 2 a p minus 1, all right? So the derivative of a square plus 1 over 2 is a. So the derivative of this guy will be p over 2 a square plus 1 over 2 p over 2 minus 1 a minus p over 2 a p minus 1. All right. So now I'm gonna write down f prime of a. All right. So how do I write it clearly? So I'm gonna put p over 2 to be the common factor. I put a to be the common factor, but here I have to reduce the power of a to p minus 2. All right. So I put p over 2 to be the common factor. Then the term inside the bracket will be a square plus 1 over 2 p over p minus 2 over 2 minus a square p minus 2 over 2. So this is not a positive quantity. But let us consider 3 intervals, right? When a is smaller than 1. What happens when a is smaller than 1? When a is smaller than 1, is it clear that a square plus 1 over 2 is bigger than a square, right? Why? Because you multiply 2 here and you get that 1 is bigger than a square, right? Because a is smaller than 1, which means that when a is smaller than 1, f prime of a is positive, right? Strictly positive. Now, what happens when a is bigger than 1? When a is bigger than 1, a square plus 1 over 2 is smaller than a square, right? Why? Because when you multiply 2 here, you're going to get 1 is smaller than a square, which corresponds to the fact that a is bigger than 1, right? So in this case, because a square plus 1 over 2 is smaller than a square, right? So this guy is smaller than this guy, which means that this whole term is going to be negative. Remember that p is bigger than 2, all right? When p is bigger than 2, if a square plus 1 over 2 is smaller than a square, then this guy is going to be smaller than this guy, and f prime of a will be negative. So if this guy is bigger than this guy, because p is bigger than 2, so the whole thing here will be bigger than the whole thing here, and f prime is going to be positive. So what happens when a is equal to 0? When a is equal to 1, when a is equal to 1, you can see that a squared plus 1 over 2 is 1, and a squared is also 1. So they're equal. So which means that this term is equal to this term, and f prime will be 0 in this case, right? So what can we say about the function fa? The function fa will increase when a is going from 0 to 1 because the derivative is positive. So the derivative is positive from 0 to 1, meaning that the function is increasing, right? So it's increasing from 0 to 1. And then because the function is negative when a is bigger than 1, so it is going to be decreased, right? So it's increased from 0 to 1 and decreased from 0 to infinity, from 1 to infinity. So the maximum will be at a point when a is equal to 1. So what is the value of the function at a point a is equal to 1? Right, so you replace it here, and you will see that this is, so what is f1? F1 will be 1 squared plus 1 over 2. So this is 1. 1 to the p plus 1 over 2. This is also 1. So f1 will be 0, right? So f1 will be 0. Right, now because the function attains the maximum value at a point a is equal to 1, you're going to have fa is smaller than f1, and this is 0. In other words, fa is always smaller than or equal to 0. Then you have a squared plus 1 over 2 to the power p over 2 is smaller than a to the p plus 1 over 2, which means that this a plus 1 over 2 to the p and a minus 1 over 2 to the p is smaller than or equal to a squared plus 1 over 2 to the p over 2, and this is smaller than a to the p plus 1 over 2. And then in this process, using an inequality, which is alpha to the p plus beta to the p is smaller than alpha square plus beta square p over 2 when p is bigger than or equal to 2. So this is going to be your homework due next week on Friday. Questions? It's good? Right. So now when you have this inequality already, when you have this inequality already, so this inequality corresponds to the fact that you pick b to be 1, but the general inequality that we need is this guy, right? So this guy corresponds to the case that we've just show for a special case p is equal to 1, right? So but this guy and this guy, they're equivalent because of the homogeneity of this inequality. Why? Because you can divide both sides of this inequality to the power p. And then here you're going to reduce to a to the b, and here you reduce to a to the b. You replace a to the b by a, and then you get the second inequality. So once you have this one, you replace each value of fx and gx into the inequality that you have here, and you integrate, and you get the inequality that we need, right? Any questions? All right. So so in the previous class, we know that, okay, so once you have this one, you can show that LP is uniformly convex in the sense that you can pick for epsilon bigger than from 0 to 2, there is a delta epsilon such that for any F and G whose norm in LP are 1, but the distance between F and G is bigger than epsilon, then the length of the midpoint F plus G over 2 is going to be smaller than delta epsilon, right? And this is how you show this using the inequality that we just showed. This is Clarkson. Right, so this is Clarkson inequality. This is important, but this is a very difficult inequality. Any questions? So if there is no questions, let us continue our discussion. All right, so right, so what we, so this is, so in the previous class, we show that for P which is bigger than 2 and smaller than infinity, then LP is reflexive, right? So basically it's uniformly convex. All right, so in the previous class, we showed that when P is bigger than 2 and smaller than infinity, then LP is uniformly convex. All right, so let us recall that from the beginning of the second half of our class, we learned about vector space and Banach space and dual space. And then we also learn uniformly convex and then reflexive, right? So we know that, okay, LP is also a vector space, a Banach space also a vector space. So LP of course has a dual space. So LP is also uniformly convex. So then there is a theorem that I don't want to show you. I don't want to prove, but you can use this result, right? Theorem. So if V is a norm vector space, and suppose that that V is also uniformly convex. So this is true for B bigger than or equal to 2 because the Clarkson inequality is true for P bigger than or equal to 2, right? So if V is also uniformly convex, then V is reflexive. Right, so this is the theorem. All right, so basically, why do we need uniformly convex? Because from uniformly convex, you can deduce reflexive, and if you have reflexive, then the dual of the dual is this vector space itself, right? So basically, the nice thing about this theorem is that, okay, so what is uniformly convex? So what is uniformly convex? Uniformly convex means that the unit ball are convex, right? Of course, with the norm, you cannot define a ball without norm, right? So the ball will be will be all of the vector whose length with the norm is smaller than 1. All right. So all of the balls are uniformly are convex. So this is uniformly convex space. But the nice thing with this is that, okay, instead of looking into the dual of the dual, what you have to do is just to look into this ball. If this ball is convex, then the space is reflexive, and then the dual of that space will be itself, right? So the nice thing of this is that, okay, to check if V star is equal to V, what you have to do is to look into the convexity of the balls, right? Now, from this theorem, what can I say about LP? P is bigger than 2. What can we say?
Just that it's
yes, Jonathan?
Just that it's reflexive?
Yes. So from this theorem, we say that LP is reflexive. Right? For P is bigger than or equal to 2 and smaller than infinity. All right? You see the point? So the nice thing of uniformly convex is that, okay, instead of showing something very complicated, you have to go to the dual of the dual. And you show that this is equal to the space that you want. This is complicated, of course, but the nice thing of the uniformly convex property is that you can look into the balls, the unit ball, for instance, and then you see if this ball is convex. If this ball is convex, then the dual of the dual, the vector space will be itself. Now, so we know that LP is convex when P is bigger than or equal to 2, right? So because of that, LP is also reflexive. Any questions? For P bigger than or equal to 2. Right? Right. So now, so number 2. Right. So you know that, okay, LP for P is bigger than 2, smaller than infinity, is uniformly convex. And then you also know that LP when P is less than infinity and bigger than or equal to 2 is also reflexive. All right. So what happened? What happened for LP with P is smaller than 2 but bigger than 1? So my answer for you is that they are also reflexive. All right. So how do we show this kind of thing? This is also not this is also complicated, but let us try to show that. I mean, at least once in your life, you see the proof and then you can use it. All right. Later on, you can use it without proving it, but at least once in your life, you see the proof. All right. So now I'm gonna consider LP, and I'm gonna show that this is reflexive. All right. So now I'm gonna map one element in LP into LP prime star. All right. So in which P prime will be the dual of P, right? So you're gonna have 1 over P plus 1 over P prime is going to 1. So I'm gonna embed LP into LP prime star, right? Why is it? So before doing this embedding, I'm gonna show you why we need this embedding. So so for 1 is smaller than 2 is smaller than 1 is smaller than p, and p is smaller than or equal to 2. What can I say about LP prime? Is it a reflexive space? Right? So I explain again. Now I want to show that LP with p is bigger than 1 and p is smaller than or equal to 2 is a reflexive space, right? So before I show that this is really reflexive, I'm gonna need some information, right? So I know that LP with p is bigger than 2 is reflexive. All right, so this is something that we already show. Now I consider the LP prime, where p prime is the dual of p, right? So in the sense that 1 over p plus 1 over p prime is 1. Is LP prime a reflexive space? Yes. Yes. So so Stephen gave a very good answer. So this is a reflexive space. Why? Right, because p prime is bigger than 2, right? So you know what? You know that 1. So so you know that 1 over p plus 1 over p prime is 1. Meaning that, okay, you're going to have p prime is 1 minus 1 over p. So this is smaller than 1 minus 2, right? And this is smaller than 1/2, meaning that p prime is bigger than 2, right? I explain again. You have 1 over p plus 1 over p prime is 1. So then 1 over p prime will be 1 minus 1 over p, and this is smaller than 1 minus 1 over 2, which is 1/2. So basically 1 over p prime is smaller than 1/2, which means that p prime is bigger than 2. So LP prime is reflexive. This is one information that we can extract from the previous proof that we showed, right? So LP is reflexive if P is bigger than 2, right? Bigger than equal to 2. Right, so this is smaller than equal. So now you know that LP prime is reflexive. Now let me recall one important inequality, one important knowledge that we learned from the previous class, which is proposition 3.20 in Brazil's book, right? So I mentioned this proposition in one of our lectures. So what is this proposition? This proposition said that if E is reflexive, and if there is an M, which is a closed subspace, linear subspace, which is a vector space of E, then M is also reflexive. Right? Now, so I recall, if the dual space is reflexive, then so is the dual. Yes. So this, so what Stephen mentioned was so yes. So this is corollary 3.21. So if E is reflexive, then E star is also reflexive, right? So this is Banach. So if you consider a Banach, if the space is reflexive, yes. So yes. So if the space is reflexive, then the dual is also reflexive, right? And then if the dual is reflexive, then the space is also reflexive. But so this is a corollary of the proposition 3.20. So to have this one, you're gonna need proposition 3.20. The proposition 3.20 said that if E is reflexive, and if M is a closed vector space of E, then M is also reflexive, right? Now, you know that, okay, LP prime is reflexive. So we know that, okay, the dual LP prime is LP, but suppose that we haven't proved that, all right? So we are in the process of proving this risk representation. So we haven't got that result yet. And we are on the way to show that, okay, the dual of LP prime is LP. But suppose that we don't know that LP prime has the dual, which is LP, right? So now we know that, okay, LP prime is reflexive. So now, if LP prime is reflexive, you're gonna need, yes, I see what Stephen means. So if LP prime is reflexive, right? So LP prime star is also reflexive, right? Which is from 3.21. So this is what Stephen means, right? So we know that P prime is reflexive, then LP prime is also reflexive, right? Now, how can I prove that LP is reflexive? I'm gonna use proposition 3.20 to show that, okay, LP is a closed vector subspace of LP prime, right? So to show that LP is reflexive, then we only need to show that LP is a closed vector subspace of LP prime star. All right, questions? I explain again this the strategies to show that LP is reflexive, right? So to show that LP is reflexive for P smaller than 1 and smaller than equal to 2, what we have to do is to create an embedding from LP to LP prime star, so that you show that LP is indeed a closed subspace of LP prime star. All right? Why is it? Because we know that, okay, LP prime is reflexive because P prime is bigger than 2, right? So LP prime is reflexive, meaning that LP prime star is also reflexive. So this is 3.21. This is something that we discussed in the previous classes. So if LP prime is if E is a reflexive space, then the dual is also reflexive. And then if the dual is reflexive, then E is also reflexive. All right. Now, to proceed further, you're gonna need 3.20. 3.20 said that if this guy is reflexive, and if you consider the closed subspace of E, then this closed subspace is also reflexive, right? Now, to show that LP is reflexive, we need to show that LP is a closed vector subspace of LP prime star. All right. Then you can use 320. Then so LP is reflexive. Any questions? It's good. All right. So now we're gonna show that LP is. So now our task will be okay. So our task will be to show that LP is a closed subspace of LP prime star. All right. So to do that, I'm gonna pick an U in LP. All right, and I'm gonna define a function T which is of the following. So I'm gonna define u f dx, ux fx dx, and I take it on d for of the function f in LP prime, right? Right. So this is gonna be ux fx dx for function f in LP prime, right? So I'm gonna for all u in LP, I'm gonna fix a u. I'm gonna fix this u, but I'm gonna multiply this u with all of the f with the f in LP prime. All right, and I integrate them on RD. So is this integral well defined? Right. So I'm gonna pick a u in LP, right? And I multiply that with all of the function f in LP prime. My question is, can I do that? Can I multiply f and u and f, and I integrate, and this integral is not infinite. Right? My question is like this. Is this integral finite? So u is in LP and f is in LP prime. Can I show that this is finite? No? Yes, Abdullah, yes. Why? Yes, this integral is definitely finite. But what is the reason? So to estimate an integral, what is the tool that you have? We have only one tool to estimate the product of two functions, right? The integral of the product of the two functions. What is it? So yes, kind of similar to inner product, but we have an inequality.
Holders?
Holder's inequality. Yes, Jonathan got it. So to show that this is finite, right? So what you do is to use Holder inequality. U in LP, F in LP prime, right? This is Holder inequality. This is the only thing that you have. This is the only tool that you have to estimate the integral of the product of the two functions. All right. So now this is finite because u is in LP and u prime, f is in LP prime. All right. So now if I consider the linear map, so fix u in LP. Now if I define this linear map, so is T continuous? So T is linear, right? Now I fix a function u in LP. I fix a function u in LP. Then I have T of f will be the inner product of f, the product of fx and ux dx. I integrate. So this is a linear function in f, right? So definitely this is a linear function in f. So can I say that this is a continuous function? This is continuous mapping? Yes, Tyler, yes. Why? This is linear, right? Excellent, Tyler got it, right? So So according to Taylor, so this is linear and this is bounded. So this is continuous, right? So we know that, okay, TF is smaller than a constant U LP F LP prime. So this is a constant. This is independent of all of the F. So this is definitely a bounded function, right? Bounded mapping. So this is linear and this is a bounded mapping because the norm of, the absolute value of F is going to be smaller than U to the P, ULP times F LP prime. So U is a constant. You can forget about that. So now F is going to be smaller than F times LP prime. So which means that this is about it linear map, right? So then this is continuous. All right. So what can I say about the norm of T? Can I borrow the norm of T? So I want to borrow the norm of T. So what is this bound?
You read out the definition.
Right. So Jonathan got it. So now, so this is gonna be the sum of all of the F in LP prime, right? Of TF dividing by F prime, right? So this is how we define the norm of a linear function, right? So this is something that Jonathan asked in the I think 2 lectures ago. So what is the norm of a linear function? A linear mapping. The norm of linear mapping will be the subprimum of all of the F in the vector space. So here, because we consider all of the F in LP prime, right? So we have to take a sum of all of the F in LP prime. The absolute value of TF is over F LP prime, right? So how can I about this? Can you estimate this norm? This norm has to be bounded by a constant. What is it? Right? So the norm will be the sum of all of the F in LP prime of the absolute value of F of T over the norm F in LP prime. All right? Now, yes. So this is the norm of U, right? Right, because you apply this inequality, right? So you have the absolute the absolute value of TF is going to be smaller than U LP F LP prime. Now you divide by F LP prime, and so of course the leftover will be U LP, right? So to summarize, what did I do? So for U in LP, right? I'm gonna associate this U with a map T in LP prime star, right? Which is LT to be integral of UF dx for the F prime in LP prime, right? And then the norm of T is smaller than U LP. All right? To summarize, for each L in U in LP, I can associate this U with a linear continuous map in LP prime star. How do I define it? I define this linear map by multiplying U with F and I integrate for F in LP prime. So this is going to be a mapping which is continuous for F, right? And then the norm of T is going to be smaller than U LP, right? But surprisingly, the norm of U of T is also equal to the norm of U in LP, right? So we show that, okay, we show that the norm of T is going to be smaller than the norm of LP by Holder inequality and by the definition of the linear of linear mapping, but my claims will be the norm of T will be also the norm of U in LP. All right. So how do I show that? So now I go back to this this definition of the function of this guy, right? And I'm gonna consider this f. So the f will be u p minus 2 times u. I consider a very special. I consider a very special value of the function f. F is going to be u p of minus 2 u, right? And then special choice. So my special choice will be f to be u to the p minus 2 times u, right? So my claim will be f will be also in LP prime. So that this mapping is well defined if I plug this value into the mapping, right? I explain again. So from the previous discussion, what we did is that, okay, for each u in LP, there is a linear map in LP prime, which is defined to be the product of u and f dx, and I iterate. So this is the linear map, and this is bounded because of the Holder inequality, and the norm of this linear map will be smaller than u, the norm of u in LP, according to Tyler, which is correct. Now, my claim will be the norm of T will be the norm of u in LP. This is surprising, but this is how we show this. I consider again this mapping. I'm gonna choose a special function, which is u to power p minus 2 times u. So my claim is that this f will be in LP prime. So who see why this f is in LP prime? Why this is f is in LP prime? Right? Show that f is in LP prime, right? So how do I show that f is in LP prime? To show this, what is the first step that we should do? What is the first step to show that f is in LP prime?
You just check that the interval is bounded.
Right. So now you write out definition and you show that that the interval is bounded. So according to Jonathan, so what we do is that, okay, we're gonna show that. So we're gonna use the definition, right? The x 1 over p prime is bounded. All right. So we're gonna show that, okay, we're gonna plug the definition inside and we show that the integral is bounded according to Jonathan. So how do we do it? So we're gonna plug u to the p minus 2 times u, and then I have p prime dx. I can forget about 1 over p prime outside because it's, if I can show this thing, then it's fine. All right. So I replace f to be u to the power p minus 2 times u p prime dx. And I want to show that this is smaller than infinity. All right. So how can I show that? So this guy will be u to the p minus 1, right, to the power p prime dx. And I want to show that this is finite. It seems to be challenging, or not? Right. So I explain again. So I consider u p minus 2 u. I claim that this is a function in LP prime. Why? Because by definition, I'm following Jonathan idea, which is correct idea. So you write out definition. You have f p prime dx to power 1 minus p prime, and I want to show that this is finite, right? So I replace f to be up minus 2u. So this gives me, so because I take the absolute value outside, so up minus 2u with absolute value will give me up minus 1. And then I'm gonna have p, I have to take the power p prime outside. And I want to show that this is finite. Any suggestion how do I show this inequality? So if you know one thing, then this is going to be direct. So what is this one thing? So to show this, you're gonna have to know what is p prime, right? So what is p prime? Now what is the definition of p prime? Right. Right. So you both got it, right? So p prime will be the dual of p, which means that p prime will be p minus 1, right? So because p minus 1 over p plus 1 over p is 1. So this is 1 over p prime, right? So we know that the p prime is the dual of p, which means that p prime is p over 1 minus p. Why? Because 1 over p prime plus 1 over p is 1, meaning that, okay, 1 over p prime has to be p minus 1 over p. All right. So now we know that p prime is p over p minus 1. Why is this interval finite? Right. So that this a very excellent answer, right? So you have u p minus 1, because here you have p prime is p over p minus 1, right? Dx. And so this gives me u to the p dx. All right. And so this is finite because u belongs to LP, right? So basically my claim is that f is up minus 2 times u is in LP prime, and the reason is that u is in LP, right? So you can show this by just writing down definition. So now you know that u is in LP. So which means that I can use this function and then I plug it into LP, into TP, right? So let us see what is going on. Right, so I have TF is going to be the integral of f dx, all right? And then in this case, f will be up minus 2u, all right? Right, so what is t of f in this case? I'm gonna multiply u with up minus 2u dx, all right? And this gives me up dx, and this is the norm of u in LP to the p, right? So this is surprising. Now, so you have TF will be the integral of u f dx, right? I replace f to be u to the p minus 2u, and so TF will be the norm LP of u to the p, right? So now let us consider TF over f, the norm of f in LP prime, right? So this is going to be u LPP, the norm of up minus 2u in LP prime, right? So we know from the previous fact that, okay, fp prime dx 1 over p prime will be u to the p dx 1 over p prime, all right? So this is what we just showed, right? So in the previous discussion, we know that, okay, if I plug f to be of this form and I take the 1 over p prime, I'm gonna get u to the p dx. But then I have to multiply. I have to take 1 over p prime outside. All right. So here I have f p prime dx will be the integral of up dx 1 over p prime, which is the norm of u in LP to the p minus 1, right? So in other words, the norm t of f over LP prime will be u to the p over u to the p minus 1. So basically this gives you u LP. All right. So in other words, this shows that sub of f in LP prime of LP prime is going to be bigger than u in LP, and this is the norm of t. So from this inequality, you have one f such that t of f over LP prime is the norm of u, which means that the norm of t has to be bigger than the norm of u. So then finally, this norm has to be the norm of u, right? So we're gonna continue our discussion on this. I'm gonna explain again this step in our next class. Any questions? It's clear? So if there's no questions, we're gonna continue our class on Friday, right? On Wednesday. And remember that we have one homework, which is this inequality, and the due day will be next Friday. All right. Good. All right. So thank you, and have a nice afternoon.
Thank you.
Thank you.
Thank you.
Thank you.